Great. So to continue our conversation about autonomous agents, we're going to start talking a little bit about flow fields. Um, Flow fields are pretty neat. You might have seen this already in a couple of other places if you have taken differential equations or done a fair bit of calculus. Uh, you may already know about the concept of a flow field. And what's really neat about fields of vectors, which is what flow fields are, as we'll see in a moment, is that it can really represent a very complex set of behaviors and forces, but can be in a way pre-computed, right? So if you can imagine, we could compute for an object the forces and things that apply to it based on its environment, or we can calculate at an environmental scale all of the forces in the various positions in the environment. Um, so why would you ever want to do this? Well, as we saw in previous lectures, to calculate the forces for a particular agent in an environment where other things in the environment affect that agent can be really computationally expensive. And so if you can bake it, or if you can take an environment and calculate all the different forces that an agent would feel in a particular location, then that agent no longer has to calculate that. And if you recall, when we were talking about flocking, the idea of calculating the set of vectors ahead of time that would then affect a particular frame and then share it across all the agents in the flock, this is kind of a similar idea, but at an environmental scale. And I think that that's really, really powerful, in particular if you, say, want to deal with a very, very large number of agents. So, for example, flow fields describe the motion of water. So say you had a particle system in a simulation that was like sand flowing through a particular medium. It's a lot easier to calculate the flow field and then apply it to millions of particles every single frame versus calculating millions of different vectors, right? It's just, instead of a calculation, it's a lookup, and that's what these things are really powerful for. So let's dive into it and talk a little bit about it. Here are a couple of YouTube. There's a YouTube link that talks a little bit about flow fields, as well as the book chapter out of Nature of Code, which I encourage you all to check out. So ultimately, an agent in a flow field. So a flow field, as you can kind of see in this image, is if you were to look at a 2D image, and then instead of looking at a equation like a particular signal, each point has an equation that's related to a particular vector. So at this position x, y, you have a set of parameters that determines it's pointing in this way. And you can kind of see that the vectors next to each other will be generally related. They're not going to be all over the place and random. Although they can be random, but most of the time these will behave and appear much like slopes, a field of slopes. And this is actually where you may have seen this before if you've done differential equations, or if you've done sufficient calculus. You may be comfortable with the concept of a derivative of a function, and a given function, a given derivative related to both the x and y axis, mapped across that entire plane, will give you a field. And then if you can kind of imagine starting with a particular differential equation, or a particular equation with a set of constraints, and then you can draw a line, and that will give you a particular solution to that field. And so if you don't understand any of that, don't worry about it. It doesn't matter. All you need to know is you need to know that this is sort of like a big group, like a big array of vectors. And the vectors tend to have some kind of relationship in some way, be it an equation or whatever. And so to apply a vector field to an agent, as you can see below, in this image, you have a bunch of these agents that are seeming to follow the flow of this. And so how do we do that? Well, what we have to do is we take a look at the position of the agent, and we look below and we see, okay, we're in this particular position, and the vector, the flow in that particular position, is there. And we apply that to the agent. as a force, or as either as a steering force or even an external force. You can kind of imagine flow to be, say you're in a pond of water and there's a rock here and it's flowing around it, and so there's water pushing on you in a particular direction, and that's unrelated to the steering force. Or it may be the steering force. So it's up to kind of the implementation. So basically, the flow just defines this mapping from a location to a vector. So you can just imagine this array again of these vectors, almost like a floor with arrows painted on them, and then you can, wherever you're standing, you look down and there's an arrow and you point yourself in that direction, and then you take one step forward and then rinse and repeat, and that's how you would kind of ultimately follow the flow. And it's quite simple. The implementation of this is really straightforward. You just have a big array, a 2D array of vectors. Generally speaking, the flow vector at that location can be a direction, but it also can be an intensity, right? So you may have a particular area where the flow is stronger, even though all the vectors are pointing in the same direction. Kind of imagine a river, right, where the speed of the water on the edges of the river tends to be a bit slower because of all of the noise, and it's bumping into itself. But in the middle of the river, the current is very strong. So these are all the vectors are pointing in the same direction, but in the middle, the vector is much stronger magnitude. So to actually apply this to an agent, right, we have our current velocity and our current future location, and then we use that to determine sort of the direction due to the flow at our future location, and we apply that to our agent, and where our max speed is this desired velocity, and that way we can calculate the effective steering of the steering force due to our future location in this way. And then we limit that steering force to the maximum force. So how do we generate these flow fields? That's a big question, right? We know that they're arrays, they're 2D arrays of vectors, so that's already, we know that that's one thing we can do. We can create an array of vectors. And also, what's the resolution, right? How big are these grids that occupies a specific thing? So to generate these direction vectors, what we can do is we can create this uniform mapping against our spacing. And let's say we wanted to create just a flow pointing to the right, then we just create this XY array, this 2D array of vectors pointing to the right. We can do this with random vectors, for example, but you'll notice that that's not super useful, and we may prefer to use something like Perlin noise, which will give us, as you can see in the bottom right image, a much more gradual and a much more flow-like flow field. And finally, we can kind of create directional things. So, based on where we are, we can rotate a vector, which would based on a particular centroid, and so we can create a flow field that pushes things away from the center. Now, this is probably the most pertinent thing. In a way, instead of visualizing a flow field like an array, in this particular case, you may want to think about it like a three-dimensional bowl in a way. So, and if you can kind of imagine this bottom image, instead of looking at this as a flat, you can kind of imagine that this is almost like having a cone, right, with the centroid being the tip of the cone, and the cone slopes down at which is the slope of which is related to the magnitude of the vector. And it's almost like if you put an object on that cone, it will slide down the cone in a way. So if you think about flow fields kind of in relation to the action that they provide, or what you can call a action potential, you may have seen things like this with the laws of physics, right? In the laws of physics, there's no such thing as a linear cone. Usually it's more like a curve of some kind, right? Like there's a hill, and if you're on top of the hill, you're always going to get, pushed down if you go in a particular direction. And more often than not, you don't have things that push away. You have things that kind of pull you in, such as gravity, right? That kind of looks like this well. So you may already kind of see the relationship between forces and these flow fields. And again, if you don't understand any of that stuff, don't worry about it. It's not a big deal, because at the end of the day, dealing with this sort of discrete place of, okay, there's just a bunch of vectors and I calculated based on these rules, no big deal. But you can kind of see how you can create extremely complicated laws of physics here without ever having to calculate them at runtime. And so you can create, say, a very complicated topographical map of different vectors and forces and things like that, like, say, a simulation of our solar system. As long as the vectors themselves don't change, which they will, obviously, with gravity. But say you have a game where you want to make sort of like an orbiting penguin. I'm sure you guys have all seen that game, right? Where you can calculate that stuff every single frame ahead of time, and then not every single frame, just one time, right? Whenever you change the size of the planets and what have you, and you can get a particularly good experience with a very complicated set of parameters and behaviors without having to do all the Kepler formulas every single frame, right? You only have to update the flow field whenever the planets or those big masses move or change in size based on the simulation that you've set up, which is a lot less than, say, 60 frames per second, right? Maybe it's every 10 seconds you update the motion of the planets because they move ever so slightly, and so on. So sometimes this makes sense, especially if you say you want to create a game where you have like a planet like Saturn and you want to simulate the rings of Saturn as particles, right? You don't want to calculate all of those laws of physics for all of those particles every single frame. So just a kind of fun relationship between this and physics. So talking about the resolution of the flow field, here are two examples, right? Like say you use 1 unity unit versus half a unit. When you have a 5x5 1 unit, you can see that here it's a lot more discrete, as in you only have so many options, whereas in the half a unit you get a lot more change and a lot more resolution. You'll find that the resolution is something you should just sort of play with until you get to the behavior that you're trying to look for. So the resolution on the left, the larger resolution, won't be able to give you these sort of fundamentally intricate motions. You'll kind of get to broad strokes in a way, because if you think about it, the key is about oscillation and jitter, like how sensitive, how quickly can we change these values. And if the boxes are too large, right, the ability for those flow fields, for those vectors to actually make a substantial effect on your object at every single frame is quite low, in particular with relationship to the change that's possible between those boxes. So say you have a box here and a box here, and one's pointing down, the other one's pointing up. Well, the next frame, if it actually has a substantial motion change, you may skip boxes, you might not be able to quickly relate those two. So in short, the overall motion will be much more broad in nature. It'll still apply a general force, and you'll still have these behaviors, and obviously, you have to take into consideration the size of your play area. So if your play area here is really just 5x5, and the grid is only 1x1, then you can't really do much except nudge the agent around in sort of like left, right, up, down. Like you can't really do too much more than that. Whereas on the right, when you have a much more dense grid, right, at every single stage, the changes could be much more subtle. And you can kind of imagine on the right, because of the much more dense grid and the ability to change things kind of more quickly, you would be able to potentially navigate this agent around in a particular path in a way that you couldn't necessarily create on the left. Like on the left, if you get it to go in kind of a circle, that's probably the most complicated thing you can get. Whereas on the right, you could potentially create some motions in that. And again, this comes down to the ability to oscillate the signal in a way because the changes are sufficiently small. Now goes to a limit, right? If your grid is too small, then you're just calculating a lot. It's a lot of memory, and the changes say that your vectors are changing really rapidly under that constraint. So you have these very, very dense things, and they're moving really rapidly. You may be moving too intimately, too intricately, and you're losing data. You might as well not do that, or you may get jitter in your signal where every single time it moves just a little bit, it's constantly being nudged aggressively. So there's always going to be the sort of just right. There's a bit of an art to this one. There's no right answer. Obviously, to the limit of this, a flow field should be continuous in general. Like you shouldn't have these dynamic, like these, non-continuous jumps in your flow field. So in theory, the smaller your resolution is, the better, because it'll just get closer and closer and closer to the actual continuous underlying equation that you're using for the differential, for the derivative flow. But it's also a performance cost and a lookup cost and a memory cost and all these things. So yeah, that's the key. Another thing you can do is obviously use spatial organization for this. So instead of actually saving the vector field, what you can do is you can use a grid to sort of create localized areas of simplified rules. So when the object's in a particular place, here there's gravity, or here there's no gravity. So you can kind of know, okay, we're here, and so let's use this equation. We're here, let's use this equation. And those equations are simplified versus having to do the whole simulation of the whole environment. So that's another way to utilize this flow field. Instead of a field of individual vectors, you have a field of different equations that are simpler than the total environmental equation. So this is kind of how you would do this. As we talked about, it's really good to create these as scripts, as individual functions at the vehicle level or at the parent class, and then the underlying objects that inherit from that class could then just call that directly, but then use and use that code in a more generic way. Or more specialized way, whereas the vehicle script is the general way to do it. And so the underlying derived script will then have to, get utilize it the way that it wants to use it, right? Say a fish is in water, so the flow is, the water. A plane is in the air, so the flow would be maybe wind speed, the air, or whatever. And then you can also create a flow field script, which would then be attached to a particular object, and that could be the flow field. That's what would generate the flow field and allow you to look up a particular flow direction for wherever your location is. So you would take that flow field and then plug it into your vehicle script. So that way you kind of have a generalized way. So say we have fish and a bunch of fish, and they can all use the same flow field instead of having to implement it at the fish level, right? Because say you have a fish, but you also have an octopus. They both want to use that same water flow, but they may have other things different in their scripts. And you can say, okay, well, I can put this into the parent class, into the vehicle, and you can, but it just is a more dynamic. It's a much more flexible architecture to take the flow field and make it its own thing. In particular, because maybe the flow field you want to load it from disk, maybe you want to use a texture, maybe you want to have it related to the terrain that you're in. So it's actually a good thing to kind of separate these two. And that's about it for flow fields. This is a very, very powerful very, very powerful mechanic to create extremely interesting and very fun behaviors in your objects, in your agents, and in your games, and in your simulations. In particular, the generation of dynamic flow fields is really cool because then you can sort of simulate rivers and waterfalls, even like a very cool things. Because imagine also flow fields can exist in 3D space, not necessarily just in 2D or even in 4D. Which what does that mean necessarily? So there's some really cool applications of flow fields, and I hope you guys all get to explore them in the projects.